Today we are going to start a very important chapter of condensed matter physics, and this is regarding X-ray diffraction and crystal structure. Actually, X-ray diffraction, which is commonly called XRD, is a very important tool for the study of structure of solids. And at present time, this XRD is used in analyzing the nanomaterials. So this is a very important experimental tool to study the structure of solids. Actually, X-ray was discovered by Rontgen in 1895, and this was a revolutionary research, because this is a very important question of general knowledge, that when Nobel Prize was started in the field of physics, the first Nobel Prize was awarded to Rontgen for the discovery of X-rays. But just after the time of discovery of X-ray, this was a vital problem, that X-rays are wave or not. This was a very important problem before the scientists. And so, two very famous scientists at the same time in 1912, Bragg and Lowe, started to question regarding this, that this X-ray is wave or not. Now it is well established that X-rays are electromagnetic wave. But as you know, the use of X-rays to determine the crystal structure is rather a simple in concept, though it is complicated in its finer details. Actually, these X-rays can be used for the study of crystal due to the diffraction experiment. But how we can diffract this X-ray? As you have studied the diffraction of visible light in your course on optics, in laboratory we use the different gratings for the diffraction of visible light. But is it possible that X-rays can be diffracted by the use of grating? Answer is no. We cannot use the simple grating which is used for the diffraction of visible light for the diffraction of X-rays. Why it cannot be used, you can understand easily, and definitely you have an idea of this. Actually, diffraction is the convincing proof of wave nature, So if you want to test that X-rays are wave or not, definitely you have to perform diffraction experiment. But as I have told you that the ordinary grating available in your laboratory for the diffraction of visible light cannot be used for the diffraction of X-ray. Why it cannot be used? First of all, we will learn about it. See this figure. I have shown here just a very simple experimental arrangement for X-ray of a wave. In this figure, actually this AB, you can see AB is actually a slit and its width is A, or you can say the size of this diffraction aperture is A. When a wave is incident on it, you can see I have shown two parallel beams of a wave incidencing on this slit. Then we know that apart from the rays which move undeviated after incidence, there are also beams which get diffracted or which get deviated from its original directions. As you can see, I have shown the beams in striking the screen at point P1 and P2. These beams are actually deviated from its original direction, as you can see the figure. These are diffracted beams, and then these diffracted beams interfere and produces the diffraction pattern on the screen. But when this diffraction will take place? As you can see, I have marked here that A is the width of the slit or the diffraction aperture. You can say this is size of the diffraction aperture, and if lambda is the wavelength of the incident wave, then our experience says that the waves are effectively diffracted only when this lambda is of the order of A. It means if the size of the diffraction aperture and the wavelength of the wave are of same order, then diffraction effectively takes place. Okay. So I have mentioned it here. You can see that A is dimension of the diffraction aperture, lambda is the wavelength of the incident radiation. And if A is of the order of lambda, then diffraction takes place effectively. Okay. Now experiment shows that X-rays have a wavelength ranging from 0.1 angstrom, 0.1 angstrom to 100 angstrom. This is actually the range of wavelength of X-ray. Okay, wavelength of X-ray, and you know that the size of the grating, or you can say the width of the grating used for diffraction of visible light is of the order of 1010 to the power 3 angstrom. Because the wavelength of visible light ranges from 4000 angstrom to 8000 angstrom. Okay, so this wavelength of X-ray is much smaller than the width of the grating, and that's why you can say that ordinary grating which effectively diffract visible light cannot be used for the diffraction of X-ray. Actually, the most suited wavelength of X-ray in diffraction experiment is of the order of 1 angstrom. It does not mean that X-ray has always a wavelength of 1 angstrom, but the wavelength of X-ray is of the order of 1 angstrom. Okay, of the order of 1 angstrom. And as I have told you that the width of the ordinary grating is of the order of 10 to the power 3 angstrom. So you can see that the width of this grating is much greater than the wavelength of X-ray, and that's why the ordinary grating which is suitable for the diffraction of visible light is not suitable for the diffraction of X-ray. Okay, I think we have understand. But as you have studied crystallography earlier, and you have seen that the interatomic separation in solids or in crystal is of the order of 1 angstrom. It means the two atoms of a solid or a crystal are normally separated by a distance which is of the order of 1 angstrom. This is order, not exact value. This may be 2 times of 1 angstrom, 3 times of 1 angstrom, 1.5 times of 1 angstrom. This is the order. So in 1912, von Laue argued that if atoms in a crystal were arranged in a periodic fashion, in a periodic manner, it means you can see if the atoms are arranged just like an array and the separation between two successive atoms is of the order of 1 angstrom, then this periodic array of atoms may serve as a three-dimensional diffraction grating for X-ray, because the interatomic separation in this case will be of the order of wavelength of the X-ray. But the atoms should be arranged in a periodic manner. Only then this will act as a diffraction grating for the X-ray. So if X-ray is diffracted by the crystals, then two things will be proved. Since you know only waves can be diffracted, so if X-rays will be diffracted, then it will be proved that X-rays are wave. And if crystals diffract X-ray, then it will be proved that the atomic arrangement in crystals are in a periodic manner. So after this experiment, these two facts will be proved, and you will be pleased to know that actually such experiment was not performed by Lowe himself, but such an experiment was performed by two very famous scientists, Friedrich and Neeping, and they were successful in diffracting the X-ray by using the crystal. Okay. Actually, in original experiment of Friedrich and Neeping, the crystal of zinc blende ZNS was used, and the diffraction pattern obtained on a photographic film consisted of a series of dark spots arranged in a definite order. Actually, such a pattern is called Love's pattern, and it reflects the symmetry of the crystal. Okay. Actually, in his research paper entitled, I have mentioned it here, you can see, Interference Effects with Rontgen Rays, von Laue developed an elementary theory of diffraction of X-ray by periodic arrays of atoms. And as I have told you, the actual experiment was performed by Friedrich and Neeping, and the experiment was successful. So after this experiment, just in a stroke, it was proved decisively that the hypothesis that X-rays are waves and the atoms in the crystal are arranged in a regular manner, these two facts were proved in a single stroke. Okay, and since then the X-ray diffraction by crystal, which is also known as crystallography, has proved an invaluable tool for measuring the X-ray wavelengths and determining the crystal structure. Okay. Now we will learn how this X-ray diffraction actually takes place. What is the real process? When you say X-rays are incident on a crystal and they get diffracted, what happens there? How you can see how you will see this diffraction? Actually, you know, X-rays are electromagnetic radiation, and its wavelength, as I have told you, ranges from 0.1 angstrom to 100 angstrom. But in diffraction experiment, the most suitable wavelength is of the order of 1 angstrom. Okay. And you know, when this X-ray will be incident on an atom of the crystal, what will happen? As you know, in an atom there is a nucleus and extra nuclear electrons. Nucleus possesses positive charge and electrons have negative charge. And you know that electromagnetic radiation means a radiation in which the electric and magnetic field vector oscillates in a periodic fashion. We generally discuss the phenomenon related to electromagnetic radiation in terms of electric field vector, not in terms of magnetic field vector, because the strength of magnetic field vector in EM radiation is very small in comparison to the strength of electric field vector. And so more or less discussion is always in terms of electric field vector. So here we will also talk about the electric field vector of the EM radiation, that is of the X-ray. So when an X-ray is incident on an atom, the electric field vector of that X-ray, which field varies actually in a periodic manner. You know, E is given by E equal to E naught exponential to the power I k dot r minus omega t. Okay, or you may also write the expression for E in terms of sine function and cosine functions, which are actually the periodic functions. So you can say that electric field of EM radiation varies in a periodic manner, and this electric field exerts force on charged particle. So when EM radiation, that is X-rays, are incident on an atom, what will happen? This electric field vector exerts electric force on the nucleus and also on the electron. But you know that electric force F is given by Q times E. Mark it. F is given by Q times E. And if Q is positive, then you know the force vector will be in the direction of the applied field. So, due to this electric field vector E of the X-ray radiation, the positively charged nucleus of the atom will experience force in the direction of the field, and so the nucleus get displaced in the direction of the field. But at the same time, if if Q is negative, what will happen? Negative charge actually experiences electric force just opposite to the electric field, in opposite direction of electric field. So the electron will experience force just in opposite direction, that of the nucleus. And that's why after interaction with X-ray beam, an atom of our crystal or solid get polarized. That is, the center of the positive charge and the negative charge get separated, as I have shown here. This minus charge and plus charge will get separated, and our atom gets polarized. Now, since electric field is not static here, electric field is varying periodically, or it oscillates with position and time. So, the dipole moment induced in this polarized atom will also oscillate. So the atom now behaves just like an oscillating dipole, electric dipole. And definitely in your course on electrodynamics, classical electrodynamics, you have studied the problem of oscillating dipole. If you have not studied it, you can watch the videos provided by me in my channel in the playlist of electromagnetic EMT and classical electrodynamics. You can see there. Actually, the atom, as I have told you, gets polarized, and since the polarizing field, electric field E, is of oscillating nature, so this polarized atom behaves as a oscillating dipole. Okay, and you know, during oscillation there will be acceleration, and whenever an electric charge or an electric dipole are in accelerated motion, the radiation is emitted by the charge or by the dipole. So actually what happens here? First of all, a radiation is incident on the atom. That radiation gets absorbed, and after absorption the oscillation starts the atoms becomes an oscillating dipole, and now it re-emits the radiation. This re-emission of electromagnetic radiation is called scattering, and definitely you have studied it. And if not, as I have suggested you, you can watch my video on this subject in the playlist of EMT and classical electrodynamics. You can see it. So I have mentioned it here. You can see the electric field being oscillatory, and oscillating dipole results due to the effect of X-rays. These atomic dipoles oscillate with the same frequency as that of the interacting X-ray. This is a very important fact of classical physics, that if the incident radiation has a frequency, let us say omega, definitely the radiation emitted by the dipole will be also equal to omega. This is a very important fact of classical physics. Okay? Or in other words, you can say that if the incident radiation is monochromatic, it has a particular wavelength and particular frequency, the same frequency and wavelength will be emitted. Okay? Now, if you are talking about a single atom, then this single atom actually re-emits the spherical waves of the same wavelength as that of the wavelength of incident X-ray. Okay, and this process or this phenomenon is called scattering, as I have told you. So this process is known as scattering. Okay, scattering from isolated point atoms is spherically symmetric, as just I have told you. But the resultant scattering from a group of atoms has a directional character. You will see it. Okay. Actually, this term scattering was used instead of diffraction by Lowe. And in Bragg's treatment, when we will study, you will see that in Bragg's treatment, the diffraction word was not used, but at the place of diffraction, reflection was used. But in Lowe's treatment, scattering means diffraction. In Bragg's treatment, reflection means diffraction. Okay. Now let us see how we can say that when there will be a group of atoms, then there will be a directional characteristic in different direction, different intensity will be produced. How we can see it? And for this you can see this figure. Actually in this figure I have shown that there is a one-dimensional row of similar atoms having interatomic spacing equal to A. All these spheres, small spheres or small dots, you can see in this figure, these are actually the atoms of a crystal. Okay, and you can see I have shown here the distance between two successive atoms is equal to A. Equal to A. This is called actually the interatomic spacing or interatomic separation. Now let us consider a wavefront of X-rays of wavelength lambda, as I have shown here. You can see is incident on the row of atoms such that the wave's crests are parallel to the row. You can see I have shown here the wave crest, and these waves crests are actually parallel to the atoms, as you can see in this figure. Okay, these are parallel to the row. Actually the atoms emit secondary wavelets. These are secondary wavelets, as you can see in this figure. I have shown here different secondary wavelets. Okay, these are the secondary wavelets you can see in this figure. Okay, and these secondary wavelets travel in all possible directions. As you can see in this figure, the reinforcement of secondary wavelets take place not only in the direction perpendicular to the row of atoms, but also in other directions. As you can see where I have mentioned zeroth order, actually in this direction the secondary wavelets reinforce one another just in a direction perpendicular to this wavefront. But here, where I have mentioned first order, where I have mentioned second order, these are the directions where the enforcement of the secondary wavelets are not in a direction perpendicular to the row. Okay. So you can say in general that the reinforcement or superposition of these wave fronts take place in different directions, not only in a direction perpendicular to the row of atoms, but it takes place also in other directions. Okay. Actually, these directions correspond to different orders of X-ray diffraction. As I have shown in this figure, zeroth order diffraction, first order diffraction, second order diffraction, there may be third order, fourth order, and so order diffractions. Okay. Actually, in these directions which I have mentioned in this figure, actually in these directions the X-ray beam interfere with one another in constructive manner and the intensity will be maximum. But there are also directions apart from these directions where the X-ray, diffracted X-rays interfere with one another in destructive manner, okay, in opposite phases. So destructive interference takes place actually in those directions. And due to, which I have not shown in this figure, and due to the destructive interference intensity will be minimum. Intensity in those directions will be minimum. Okay. And so you can say that it may be possible that reinforcement take place in some particular directions only, whereas in other directions the wave fronts interfere destructively and the intensity is minimum. Actually, such enforcement produce lowage pattern. Actually, when you are talking about lowage pattern, that means the pattern where intensity is minimum, not maximum. But the pattern which is obtained, which are for maximum intensity, they are actually Bragg's pattern. In Bragg's pattern, we talk about the maximum intensity, but in Lowage pattern, we talk about the minimum intensity. Okay. But as you can see, I have actually considered here a linear lattice, or you can say a linear arrangement or one-dimensional arrangement of atoms to understand the actual process of diffraction of X-rays. But in actual practice, the X-rays are not an array of linear atoms, but this is a this has actually three-dimensional structure, or you can say that in actual crystal the problems will be from a three-dimensional array of atoms. And so when we talk about the actual crystals, the problem is some more complicated because of the presence of three-dimensional arrangement of atoms, not such simpler. Actually, the conditions a crystal to diffract X-rays can be determined by using, as I have told you earlier, either by Bragg's treatment or von Lauw's treatment. And in the forthcoming lecture, we will separately see the treatment of Bragg for X-ray diffraction and von Lauw's treatment of X-ray diffraction. Okay. Both will be dealt separately, and actually those are actually the very important concept. Actually, which I have explained here, all those things I have marked here, I have written here in brief for your convenience. I am just giving the reading which I have written here, for your convenience, although I have already explained this. I have mentioned it that consider a one-dimensional row of similar atoms having interatomic spacing A. Let a wavefront of X-rays of wavelength lambda be incident on the row of atoms such that the wave crests are parallel to the row. All these things you have learned. The atoms emit secondary wavelets which travel in all possible directions. The reinforcement of secondary wavelet takes place not only in a direction perpendicular to the row of atoms but also in other directions. These directions correspond to different order of X-ray diffraction. The zeroth order, the first order, the second order diffraction directions have been shown in the figure. In other directions, the wavefronts interfere destructively and the intensity is minimum. Such reinforcement produce low wedge pattern. Okay, so I think uh, this was just a brief introduction regarding the X-ray diffraction. Although such type of questions are not asked in your examination, but for further understanding of X-ray diffraction, the actual problem which we will deal, this is very important to know. What is the history behind this? Why X-ray diffraction is used to study the crystal structure, and how you can say that X-rays, which are electromagnetic radiation, can be diffracted only by using the single crystal. The ordinary grating cannot be used for it. So this was just a brief introduction, and I think you have definitely enjoyed this introductory lecture on X-ray diffraction. Now in the forthcoming lecture we will start to deal with the real problem. First of all, we will see Bragg's treatment of X-ray diffraction. Then we will see the low wedge concept. Okay. Thank you very much.